Albert Einstein famously stated, "Look deep into nature and then you will understand everything better." Little did scientists know that the key to understanding the surrounding world was by literally looking deeper into nature, straight into the quantum realm. Quantum, a word which we all have heard of at least once in our lifetimes, and we have immediately realized it holds a great ton of weight. However, the true definition of this word, ironically, does not refer to something which is as heavy as it seems. Truly, it refers to something which may as well be one of the lightest things in our universe. Literally. Previously, Newtonian physics explained some of the macro objects of our universe. However, when things got small, such as within an atom type small, things got really funky. No, not that kind of funky, but in fact, really interesting. Very recently, a few applications of this technology have been explored, and scientists have encountered ways to use these technologies towards building supercomputers through the use of something astonishing, the quantum computer, and more importantly, at its core, the qubit. In order to understand the application of quantum mechanics in quantum computers, one must first understand three main principles of quantum mechanics. This includes quantum spin, superposition, and entanglement. Firstly, you have quantum particles, or in essence, small particles of our universe, which, such as electrons, which are magnetic dipoles, which create a downward-facing magnetic field upon spinning one time. This property of spin is defined as up or down. When a particle, such as an electron, spins one way, it is said to be in spin down, and as it switches directions, it can be said to be almost it turns around, and it is thus in spin upward position. As explained ingeniously by Professor Morello, an externally magnetic field can be run around the particle, and this particle will essentially align itself in its lowest energy state, which is during the face down, and which is when it is aligned along the magnetic field. This is similar to if you're riding a canoe down a lake. If you're with the tide, it'll be much easier. You're in your lowest energy state as you use less energy. However, if you're against the tide, it'll take a lot more energy and it'll be much harder. Next up, we have superposition. Superposition infers that we do not actually know the state of a particle. The particle is in all possible states simultaneously, meaning it is in spin up, spin down, spin left, spin right. It is at 60 degrees north, 60 degrees south, and all possible states all at the same time. And a quantum particle is in all of these states until it's measured, at which point it finally chooses a specific state. Well done explaining superposition, Professor. Now for an example. For example, if I were to turn off the lights,
I could currently be in the room, not in the room but turned away from the camera, or perhaps in the room and turned towards the camera. Everything is possible. And let's give it a try by turning on the lights. And you'll notice that I have to instantaneously make a choice of what position I have to be in, as turning on the lights is simply a form of measuring my position. Oh wow, would you look at that? My position is facing away from you. So by turning on the lights, you simply measured my position. But before that, I was in all possible positions at the same time. Let's try it once again.
oh, would you look at that? This time I've ended up in a different room entirely. Let's try it once again. Oh wow, would you look at that? Back to normal. And similar to the amount of times I had to choose a position instantaneously, even a quantum particle is in all positions at the same time, and simply chooses a position once measured. And finally, we have entanglement. Entanglement is best described when you consider two quantum particles working together, so two electrons, and is best described as a particle which has no state of its own, but in fact, its state is what is the exact opposite of its entangled particle, or the particle it's paired with. For an example, let's head back to Coco. Hey, where are you off to? Oh, I'm headed upstairs. Oh, I'm going downstairs. Really? I think it's kind of cold here. Oh no, it's really warm in here. I think I'm going to go outside and get some fresh air. No, I think I'm going to stay inside. Okay, well, similar to the enactment you just saw, quantum particles can always be the opposite of one another. Einstein referred to this instantaneous decision-making process of the particles as spooky action at a distance. Because it's not simply like tossing a coin, where you're dealing more with probability. Quantum entanglement deals with simply the analysis of a system at a specific point, meaning truly the particle is in the superposition state, which we were talking about earlier. And it's in all the states at the same time. And it's when we analyze one particle that the other particle makes a decision of what it has to be. Meaning if this is up, this will be down. But if this is down, this will be up. But it has no position of its own. So overall, all these principles come together to form a modern-day pinnacle of innovation, the qubit, which runs based on all of these principles, and may possibly even prove to be becoming an amazing technology which is exponentially faster and exponentially more efficient. It also has a variety of applications, from factoring large numbers and improving security systems to possibly even developing artificial intelligence. Thank you very much for watching my video.